the original tree. So I'm going to draw the original one, 0. There is a note here. And then there is another here. So this was 1, 0, 1, 2, 3, and 4. So these two connected. This was connected to this one. I guess that's also this one. So this is our original tree. We want to apply the DFS here. So we start from the 0. From 0, we went to the first child that has a lower index, so was 1. So we went to 1, just drawing the 1 as a child. And then from 1, we go to its children that which we haven't visited, and the lower index is going to be 2. And then from 2, we're going to go to another child. It's going to be 3. So we go with one depth completely. 3 doesn't have any unvisited children. We go back to 2. 2 doesn't have unvisited children. We go back to 1. And 1 does have one unvisited child, and that's going to be 4. So we're drawing 4 here. So this is going to be the tree of this, as this is also kind of spanning tree of this graph using a DFS algorithm. And so you can imagine if you're going, in different direction, your tree is going to be different look. But one thing is like kind of obvious is that it's showing definitely has its own application. It's showing us definitely if there is a disconnection, and also it's showing us also like you see like 0 and 3 are directly connected to each other, but in this algorithm it's kind of show them as far, right? So very far from each other. So in this tree, so we basically it has a lot of applications. So let's look at the applications of using the DFS to traversing the tree. So detecting whether the graph has disconnection or not, detecting is there is a path between two nodes or not, finding a path between two nodes, and also finding cycles, detecting cycles, and so on. So it has those applications. So BFS is also another algorithm, and that also has a lot of application, and it's also going to create a tree for us after we're traversing the tree using the BFS. But BFS is going to be level by level, right? So, and we always talk about how we can implementing the BFS using Q and ask you to try to do that yourself. Well, here is like a pseudo code for it. So we have a queue, and we're going to add the nodes to the queue. So I guess, again, same idea. We don't have really a root. Just pick one of the nodes as the root, and we're going to start finding all of the children of that particular node. And we add them all to the queue. And then when we basically visit them one by one from the beginning of the queue. And as we visit them, we're going to find the children of them as well and add it to the queue. And we keep going until the queue is empty. So now let's apply that to this example that we had already. So I have to draw this again. So 0, 1, 2, 3, and 4. This is a little bit, I guess, different, maybe. Okay, so now we're going to do the same thing. This time we're going to use BFS, right? So BFS algorithm, as I said. So we started from 0 again, just the index 0, and then we're going to find all the children that are immediate children, basically, to that. So the children are 1, 2, and 3. We add them to our queue. So we make the 0 visited, we go to 1, and we find all the children that are not visited or they're not on the queue for 1. So we're finding 4, and we add it to the queue. So we go to the 4, we go to 2 now. We're trying to find all the children of 2 that are not visited, but there's nothing there. And then we're going to 3, I'm going to do the same thing, there's nothing there. And we're going to go to 4, and we're going to do the same thing, there's nothing there to be added to the queue. So this is going to be the result of the BFS of this basically graph. So it's creating a tree, is a spanning tree, but it's going to be different. The DFS traverse. Let's do the different DFS traverse of this one, because the graph is a little bit different from what we had. So we're starting from 0 again. So this is going to be the DFS of the same. So I'm just going to separate them. So that up one is the BFS. Now I'm going to do the DFS. We start with 0, and we're going to go to 1. And then we find all the, we go to children with lower index of 1. So we go to 2. We'll go to children of the lower index of 2. We're going to 3. And we're going to children of the lower index of that. And that's going to be 4, right? So because 4 and 3 in this example connected to each other. And so 4 doesn't have any children that we haven't visited. We go back to 3. 3 doesn't have any children that we haven't visited. So we're going to go to 2, same thing to 2, 1, and we go back to 0. So it's going to create a really kind of a funny or kind of linear tree. So that's the DFS tree of this algorithm. That is the kind of tree, right? We can have those as a tree as well. Okay, so back to these are also the applications of the BFS. Definitely, it's going to give us the shortest path. So, and you can see that in the example too, right? The shortest path from, going to 0 to 4, for example, is going to be directly going to 1 and then 1 to 4. So that's obvious in the tree that the span tree that it's going to be generated. So it's going to give us the shortest path as well between 2 nodes. The DFS is only going to tell us there is a path, but the BFS is going to find the shortest one. So we're also going to talk a little bit about the weighted graphs as well. So the weighted graphs, they do have some sort of weight on the edges. Those weights are they're not negative weights, right? So they're real numbers. And when we have a path, what does path means, right? We want to go from we already talked about the definition of path inside the tree. That's the same definition. From one edge, we're trying to go to from one node, we're trying to go to another node. And in order to go that, we have to pass through some of the edges. So we're passing some of the edges. And we, in the weighted graph, we add or we sum up those numbers of the weights on those edges that we have to pass, and that's going to give us the shortest path. So we find multiple paths, we add all the weights on each passes on the and add them together and see which one is going to give us the shortest weight value, and that's going to be the best and shortest path. Shortest path in the weighted graph doesn't mean the shortest number of edges. Is actually means the shortest number of weights on those edges as well. So maybe we only connected through one edge, but the edge is the weight of the edge is very high, so it's not worth it. We'd rather go from a different road or from a different path, and which helps us to have a less basically weight. So here we're going to talk about this short path algorithm, and we're going to see an example of it and how this is going to be helping us basically. So this algorithm giving us the smallest weight, that's how it's going to solve the problem. And it's kind of like a greedy algorithm. So it's going to all the possibilities and then finding the minimum one. So here is the algorithm. So we start from the initial array, and we have to go through these steps, and we have to, you know, this only gonna give us for one of the nodes that we just started with it. From that node to the other nodes is going to give us the shortest path. But we have to, if you have n nodes in the tree, you have to repeat this n-1 time for every single basically nodes, so we can find the shortest path for all of them. So this is going to be the shortest path for just one of them to going to the other. So this is an example that we're going to use for this problem. This is going to be the basic, as you see, also not only weighted but also a directed graph. So then to make it a little bit more interesting, so it's weighted and also directed. So where we're going to start with an algorithm, this is how we're going to start. First, we're going to create an array list of smallest weights. So we're going to put some of the weights first, and then we have another array that originally everything is false. It's just kind of Boolean array, the number of nodes, and it's the weight that we find. And whenever we know that we find a weight for one of them and are already we're done with that, then we're going to make it true. So the index of the nodes, we put the indexes, so 0, 1, 2, 3, and 4 are the indexes that we have. So I'm going to try to draw exact same thing. The whiteboard, and then we're just following this algorithm using the whiteboard so we can get the result from there. So hopefully that would be a good idea and helps us a lot. So let's try to draw that. Now that we have this, I'm just gonna use those arrays that we have there. You're gonna draw the same thing here, basically. So we have the first array that's giving us the index of, this is for weights that we find. So this is the Boolean one, and this is going to be the original one. And so that is going to have the smallest one that we find so far, and it's going to be from index 0 to index 4. So I'm trying to draw that. So 0, 1, 2, 3, 4. And then same thing here. So I didn't do it. Very good job, but then that's good enough, I guess. Okay. So at the beginning, they're all going to be false. Just the first one is going to be true. And that's because we start from index 0 to 0. It's 0, right? We already know the weight for that one. And the rest are going to be false. I'm just going to put the false here. From 0 to 1, I know the index is 16, so the weight is 16, so I'm putting 16 there. 0 to 3 is 2, so I know that one for sure, 2. And from 0 to 4 is going to be 3, so I know that as well. We don't have a direct basically path from 0 to 2, so here, based on the algorithm, we're just going to use the infinity. So that's for us is infinite. We're going to go to the second round. So the second round, we're going to see that what is going to be the lower index here, right? So the lower one is right from 0 to 2. So that's going to be the shortest path for me. And so this weight here, when I get from 0 to 3, the weight for this is going to be 2 already, right? So we already have plus 2 here. So now from this, from 3, I come from 0 to 3, and then from 3, if I want to go to 1, it's going to be 12 plus 2. It's going to be 14. So it's going to be lower than 16, right? So directly, if I want to go directly, it's going to give me 16. But if I go to 3, and then from 3, I go to 1, it's going to give me 14. So that's less. So I'm going to change that to 14. Then I'm trying to go to 2. So if I go here, and then from here, I try to go to 2, I can still go because I don't have a direct connection as well over there. So that is still going to be infinity. And then I'm trying to go to 3. That's become, this we stay the same. So that's the smallest one. That's 2. And then from there, I'm going to try to go to 4. So if I want to go to 4, it's going to be 7, and 7 plus 2 is going to be 9. So it's going to be a lot more, right? So just can directly go, it's going to be 3. So that's not a good idea. So that's not going to change. But we already visited the E, right? So this become true here. And we're done with that. Then we're going to go to the next one. I'm going to use another color, and we're going to go to this array, and we're going to find the smallest one here, which is now going to be 4. So that means I go from 0 to 4. The weight here is 3, so that means I'm already plus 3, whatever I'm going to do. And now from 4, I'm going to go back. I'm going to go to 1. It's going to be 10. Plus 3 is 13. So whatever I had so far was 14 and 16. So this is much better. So I'm going to change that to 13. So that means I'm going to go from 0 to 4, and then from 4 to 1 is going to be a lot cheaper, right? Or shorter, or smaller, as far as the weight. Then I'm going to try to go to 2. So we do have a direct connection to 2. So I can now go from 0 to 4, which is 3, and then from 4 to 2, which is going to give me 7. So now we finally we find a better number. So that's 7 now. Then we're going to go to 3. So here to here is 3, and then I can go from 4 to 3, which is 5. Then the total is going to be 8. But I was able to do it with 2. So that's not a shortest or smallest one. So I'm not going to change anything there. And the last one is the 3. So I'm just going to change this to true as well. Then we're going to go another round. So this time, again, searching to these numbers, I have 0, 13, 7, 2, and 3 already visited. So 7 is going to be the smallest one at this point. So I'm going to pick that. And that means I go from here to here. And then I go from here to here. And that's already going to give me plus 7. Now from 2, I like to go to 1. So that's 7, and I have another 3. That's going to give me 10. So it's a lot better than 13. So I'm going to change that to 10. Then from here, I like to go to 3, so that's definitely going to be more expensive, so that's not gonna worth it. And then from the 2, I want to go to 4. So again, that has to be 7 plus 3, and then I mean that's basically not going to worth it. So you're just gonna leave it like that, and we're going to make it to be also true, and we're basically calculated the weight for that one as well. So now that the results we have is 0, 10, 7, 3, and 4, and that's exactly the shortest path from 0 to every other nodes inside the tree. So that's why you have to do this algorithm for all of them one time, and we're only going to show you one round of it. And the next one is going to be, the only thing is left for us is going to be the index 1. So I already know in order to get to 1, I better to, I'm just going to change my color to, I'm going to use red this time. So I know that for this, the best way to go is going from here to here, and then from here to here, and then from here to here. And that's going to give me plus 10 already, right? So that's the weight that I have until I get to this point from 0. Now, if I want to go to any of the other nodes, basically it's not going to give me any better option. So 10 is the best possibility, and nothing else going to change. So I'm going to say that this is also true, and we're done. So we find a weight for all of the basically nodes. So from 0 to 1 is 10, from 0 to 3 is 2, from 0 to 4 is going to be 3, and from 0 to 2 is going to be 7. And I find the shortest path from 0 to all of them. So I have to keep repeating that for 1, the next time for 2, same exact thing with it here, until we find the shortest path for all of the nodes. So that's also the shortest path algorithm. Again, we're not going to ask you to do any coding on the graph, but sometimes concepts like it's nice to be able to implement the BFS, DFS types of algorithm using it, or just think about how you can implement the DFS and BFS. So just the idea was introducing the graph, and know that graphs have some very important application, helps us to solve a lot of problems in computer science or in other disciplines.